there, welcome back. In today's lecture, we're going to talk about state and output feedback. So these are two fundamental methods for controlling systems, okay? Now, as opposed to previous lectures where we've talked more about analysis techniques, in this lecture, we're actually going to discuss control synthesis techniques, okay? So this is an exciting time in the course. We're finally getting to be able to design controllers for our linear systems. Okay, let's get right into it. All right, so I'm going to start off by talking about one full state feedback. So let me set up the problem of full state feedback, what our goal actually kind of is. So what we're going to do is we're going to consider a linear time invariant system, right, which is a state equation x dot equals ax plus bu. I'm going to ask, how should I pick my input u to best stabilize the system, right? So, we talked about stability in the past, right? And we said that, okay, if we have a system of the form x dot equals ax, we can come up with all of these nice conditions where, the equilibrium xe equals 0 is globally exponentially stable, right? And so on and so forth. Now what I want to do is I want to use this input u, which, is entirely in my control, to kind of shape the dynamics of the system, right? I want to pick a really nice value of u that will actually drive my system to be stable. So what am I going to do? Well, in the case of full state feedback, I have a couple of assumptions that kind of make this problem nice. So we assume we have full knowledge of our state, x of t, at all t in R, or at least R greater than or equal to 0. Okay? So we assume that we always know our full state of our system. Now, as a consequence of this, we can actually design controllers that incorporate knowledge of our full state, right? So, if I want to drive my system to the origin, well, it kind of makes sense that I should adjust my control input depending on where the state of the system currently is, right? So in general, what I'll do is I'll determine what we call a control law, which is essentially a rule that maps from my current state x to my input u equals k of x, such that the equilibrium point xe equals 0 of x dot equals ax plus b times k of x has some mode of stability, okay? So I'm trying to pick a control law, u equals k of x, that renders the equilibrium xe equals 0 stable, right? Or maybe asymptotically stable, or globally exponentially stable, or one of these modes that we talked about earlier in the class. So how exactly am I going to do this? Well, what should this function k be? Well, it's pretty clear right away. If we just pick some sort of arbitrary nonlinear function, all of the analysis tools that we picked so far in this course won't really hold up, right? So if k is nonlinear, then we need nonlinear analysis tools to study x dot equals ax plus b k of x, right? And its resulting stability under this control law k of x. So what are we going to do? Well, kind of take a moment and see if you could figure out a really simple control law such that this closed loop system, right? So closed loop system, which is the system with my control law plugged in, is actually easy to analyze given the techniques that we've discussed in this course. So take a moment to think about that. Okay, so I'll assume that you've kind of given it some thought. Now, a basic idea, which is called static linear state feedback, or full state feedback, is essentially we pick a control law u equals k times x, right? Where k belongs to Rm by n is called a gain matrix. Okay? So instead of picking some arbitrary nonlinear function, k of x, right, we just pick a matrix, k, which is fixed, right? It's static, it doesn't change with time. We just multiply that by our current state, x. Okay, so let's see if we could kind of figure out whether this kind of nice static linear full state feedback control law actually gives us what we want. Let's go ahead and plug it in, right? If we plug this into our system, we get x dot equals ax plus bu, which is bkx, right? If I factor out an x, then I get x dot equals a plus bk times x. So my question is now, if I want to render this system, let's say, globally exponentially stable, what I want to do is pick the value of k such that a plus bk has stable eigenvalues, okay? So my question is how to pick k such that a plus bk is Hurwitz, okay? Or has stable eigenvalues. So this question is really essential to figuring out how to do basic linear control design, right? So this is a really simple example of a control law, right? U equals k times x. And I'm saying, all right, maybe under certain conditions on my system, this really simple control law is actually sufficient to buy me global exponential stability. Okay, so when can we actually use this matrix K to get global exponential stability? Well, given kind of what we've said in previous lectures about controllability and observability and stabilizability, you might kind of think that there's some sort of relationship between all of these concepts, right? Being able to stabilize my system and, say, having the system be stabilizable, right? Surely it seems like those two properties should be related. What we're kind of going to piece together over the course of this lecture is that stabilizability is actually exactly the condition we need to be able to stabilize our system from feedback u equals k times x. Okay? All right. So let's try to work out what these conditions are under which our system can actually be stabilized via the state feedback u equals kx. Right? We've just said that we have a kind of hunch that the right conditions are stabilizability, but how do we actually arrive at that condition? Well, let's start off by analyzing this problem of showing a plus bk as Hurwitz. So when is a plus bk made Hurwitz by a choice of k? Okay, this is what we're going to try to answer. So a nice place to start to kind of figure out what an answer to this question would be is to analyze the characteristic polynomial of a plus bk. Okay, so let's start with the characteristic polynomial of a plus bk, right? Because we know that the roots of this characteristic polynomial precisely give us the eigenvalues of a plus bk. If we're able to figure those out, then we can kind of directly tell if a plus bk is Hurwitz, right? Okay, so let's write out the characteristic polynomial. So we have chi a plus bk, evaluated at s, is equal to the determinant of si minus a minus bk. And let's say that, we have some coefficients that, are functions of k that kind of give us this characteristic polynomial, right? So this will be equal to, let's say, s to the n plus some function an minus 1 of k, s to the n minus 1 plus all the way down until plus a naught of k, right? So each of these coefficients depends on k. So here's the basic idea. If we want to be able to stabilize a plus bk, right? If we want to be able to make a plus bk Hurwitz, it's sufficient to have arbitrary control over my coefficient functions ai of k, right? If I can pick each ai of k to be whatever I want, as a function of k, then I can arbitrarily control the coefficients of my characteristic polynomial. And if I can arbitrarily control the coefficients of the characteristic polynomial, then I can put the eigenvalues of the system wherever I want, right? So if we can do this, we can put the eigenvalues of a plus bk wherever we want, and therefore we can make a plus bk Hurwitz, okay? So this is our basic design principle, right? If we can completely control each coefficient of the characteristic polynomial, then what we could do is we can pick each coefficient such that the characteristic polynomial has all stable roots, right? Okay. So what's a problem with this method? Kind of take a moment and see if you could figure out what this, kind of might be. All right, so I'll assume you've given this some thought. One of the main problems is that the relationship between k and the coefficients ai is very nonlinear, okay? Very nonlinear. Further, it's really, really hard to actually compute the actual roots of these polynomials in general, right? I don't know what the largest matrix you've ever solved for the eigenvalues of was, but, it really takes some time to figure out eigenvalues and roots and so on and so forth when we're calculating all these things, right? So what do we want to do? Well, let's see if we can transform a system into a form where characteristic polynomial chi a plus bk is easy to compute. Now further, we want the relationship between k and ai of k to be transparent. Okay? So instead of having these really messy relationships between this gain matrix K and all the coefficients of my characteristic polynomial, I want a really nice and simple, easy relationship, okay? I want it to be easy to figure out. Now further, I also want my characteristic polynomial to be easy to compute, right? It shouldn't take a lot of work to actually work this thing out. Okay, so let's go ahead and start with this first problem over here, figuring out a form of matrix where the characteristic polynomial is easy to compute. The basic idea is, if we can transform our system into one of these forms, then we could figure out its characteristic polynomial fairly easily. Okay, so what I'm going to do is I'm going to start out by defining something called a companion matrix. And this is a class of matrix in which the characteristic polynomial will be really particularly easy to compute. Okay, so definition, which is the companion matrix. So we say that a matrix A in Rn by n is a companion matrix, or sometimes we'll say it's in companion form. Companion form if it's of the following form. So we'll have A equals 0, 1, 1, 1, A0, A1, A2, all the way up until AN minus 1, okay? And then we have zeros everywhere else. 0, 0, 0. Okay, so basically a matrix is in companion form if it has ones just above the diagonal, some sort of non-zero coefficients all along this bottom row, and then zeros everywhere else, okay? Where each of these coefficients is just some real number. Okay, so why do we want to introduce this class of matrix in particular? Well, it turns out the characteristic polynomial of this matrix is really, really easy to find out, okay? We could basically just read it off directly from the structure of A. All right, so let me just state this as a lemma, which is the characteristic polynomial of a companion matrix. Okay, so I'll say let A in Rn by n be a companion matrix. Okay, I'll assume that it's just of the form above. Then its characteristic polynomial is computed. Chi A of S is equal to S to the n minus AN minus 1, S to the n minus 1 minus A1 times S minus A naught. Okay? So basically what happens is that each of these coefficients just has its sign flipped and then directly appears on the corresponding power of S in this characteristic polynomial, right? So A naught gets its sign flipped to minus A naught and corresponds to the power S to the 0, right? A1 gets its sign flipped to minus A1 and corresponds to the power S to the first, okay? So this makes it really, really simple. So really simple to determine the relationship between the matrix entries and the characteristic polynomial coefficients. Okay? So, this really kind of stands in opposition to the general case where it's a huge mess to determine, where these different characteristic polynomial coefficients come in. Okay, so just as a quick side note, the proof of this is just an application of cofactor expansion. So this is a nice exercise to try. I just won't do it here just for the sake of time, okay? But I'll include a proof in the notes. All right, fantastic. So like we said, matrices that are in companion form have a really transparent structure, okay? So what I'm going to do now is I'm going to consider a SISO LTI system with state equation x dot equals ax plus bu, okay? So I'll say that A is in companion form. Now what I want to do is I want to figure out a B matrix for this SISO system, right, where U is a scalar, such that it's really, really easy to work out the relationship between my gain matrix K and, this matrix A plus BK and its characteristic polynomial, okay? So what I'm going to do is I'm going to say, consider the B matrix B in Rn by 1, since we're SISO, and it's going to have zeros everywhere, but in the last entry, we'll have a 1, okay? So how is A plus BK computed for such a matrix? Well, if we're in companion form, right, we have zeros, ones, then we have an A naught, A1, all the way up until AN minus 1, and this will be plus this matrix B, which is zeros, then a 1, and then a gain matrix K, right, where K belongs to R1 by N, right, so we'll have a K naught all the way up until Kn minus 1. If I compute the sum, right, what I'll find is that my resulting matrix, A plus BK, is actually still in companion form, right? So now I'll have A naught plus K naught, A1 plus K1, all the way up until AN minus 1 plus Kn minus 1, okay? So if I compute the characteristic polynomial of this system, chi A plus BK, right, I'll find S to the N plus, minus AN minus 1 plus Kn minus 1, S to the N minus 1, all the way down until this A naught plus K naught term, okay? So here's the basic idea. When A is in companion form and B is equal to zeros and then a 1, it's very easy to determine the relationship between your gain, K, which is in R1 by N, and the coefficients of the characteristic polynomial of A plus BK, right? Now again, this is only in the SISO case, right? It turns out, there will be a kind of similar structure in the MIMO case, which I'll very briefly talk about a little bit later. But basically, when we have A and B in this sort of structure, it becomes really, really easy to solve this problem of designing my gain matrix K to produce a stable system, right? Because over here, it's pretty clear that I have complete control over every single one of these coefficients in the characteristic polynomial, right? For example, I could just pick Kn minus 1 to be minus An minus 1 plus anything that I want, right? So really, when we're in this form, it becomes pretty clear that, this problem of selecting a gain K to stabilize my system is actually something that's solvable. Okay, so because this form is kind of important, we give it this special name, which is called the controllable canonical form. So definition, controllable canonical form. This is sometimes abbreviated as CCF, okay? So what I'll say is consider a pair A comma B, where A belongs to Rn by N, and B belongs to Rn by 1. Okay, so this is still a single input system. So we say that if A and B are of the form A equals 0, 1, zeros, 1, and then we have an A naught, A1, A2, AN minus 1, and then a B, we just put zeros over here. And then my B matrix is going to be zeros, and then a 1. Then we say AB is in controllable canonical form. Okay? So what we've effectively said above is that if the system is in CCF, this K matrix can be chosen to arbitrarily assign coefficients of chi A plus BK. Okay? All right. So here's a really nice fact from linear algebra that'll actually make this really useful for us. So fact is that for any matrix A in Rn by n, you have that T inverse AT and A have the same characteristic polynomial. Okay? So if you transform a matrix into a new basis, right, by doing the similarity transform T inverse AT, you don't actually change the characteristic polynomial. All right? So what this means is that if we're somehow able to transform our system into controllable canonical form, right, where it's really easy to go ahead and compute this characteristic polynomial of A plus BK, then, maybe it's going to be really easy to solve this control design problem for that arbitrary system. Okay? So let's go ahead and see if we could figure out when we could transform our system into controllable canonical form. Now it turns out, as this name CCF kind of suggests, we could perform this transformation exactly when our system is controllable. So let's go ahead and prove that. So this brings us to the following lemma, which is transformation into controllable canonical form. Okay? So we'll say consider a pair AB where A belongs to Rn by n, B belongs to Rn by 1. Actually, I won't state that it's in controllable canonical form yet. Okay? All right, so let's state two conditions. So first, we'll have 1, CCF is controllable. Okay? So if A comma B is in controllable canonical form, then AB is a controllable pair. Okay? So CCF implies that you are controllable. Okay. Now second, we have transformation into controllable canonical form. Okay. So what this says is that A comma B is a controllable pair if and only if there exists a transformation T in Rn by n such that A tilde B tilde, where A tilde is equal to T inverse AT and B tilde equals T inverse B, is in controllable canonical form. Okay? So it turns out every single input controllable system can be transformed into controllable canonical form. And in fact, this gives us a one-to-one characterization of controllability for these systems. Okay, fantastic. So let's go about proving this result. So proof. So item 1. This is something that follows from computation of your controllability matrix. Okay? So this proof is just fairly computational. I'll just give you a quick sketch. In the simple case where A equals 0, 1, and then zeros all the way over here. So this is a simple case. So in this case, what you could show is that your matrix CAB, when B is equal to zeros and then 1 at the end, will be equal to just ones, kind of moving up the diagonal like this, and then zeros everywhere else, okay? So this is just kind of shown by this multiplicative structure of A and the fact that B just picks out the last column, okay? All right, so this is in fact a full rank matrix, and controllability follows, okay? So the general case is a similar result. We'll just find out that we'll get some non-zero terms kind of hanging out down here, okay? All right, fantastic. So that's a kind of quick sketch of case 1. Now case 2, I want to give a more thorough proof of this. Okay, so what are we going to do in case 2? Well, we recall the fact that A and T inverse AT have the same characteristic polynomial. Okay, so it'll be a very useful fact for us in this proof. Okay, so using this fact, what are we going to do? So how can we figure out A tilde based on this fact? Well, think about this for a moment, right? A tilde is this matrix that we want to put in controllable canonical form, right, which requires that A tilde be in companion form. Now, if I tell you that A has the characteristic polynomial, chi A of S equals S to the n plus an minus 1, S to the n minus 1 plus A naught, what does that tell me that my controllable canonical form of A needs to look like? All right, just think about this for a moment using this property that we had discussed up here, right? And, if we take a look at this lemma, right, what we'll find is that what we should have is A tilde equals 0, 1, 1, minus A naught, minus A1, all the way up until minus A sub n minus 1, okay? All right, so this identifies what our A tilde should be, right? Then our B tilde, just by the standard CCF, should be 0s, 0, and then 1. Okay, so now we at least know what we need to transform our matrix A into. Let's kind of see where we should go from this, right? So what do we do? So our general strategy in this proof will be to transform both A and A tilde into a form that is almost controllable canonical form. Okay? So it's a form that looks really close to it, and we want these to be the same, okay? Then what we'll do is we will back out the transformation from A to A tilde, okay? So what I'm going to do is I'm going to take A and A tilde and transform them into an intermediate form in which they're the same, right? Then after this, using that those intermediate forms are the same, I'll be able to back out this transformation into the form of A tilde. Okay. So how do we get this intermediate form? Intermediate, almost CCF form to be the same for A and A tilde. Well, what do A and A tilde have in common? Well, we at least know that A and A tilde have the same characteristic polynomial. Okay? So if this intermediate form only depends on the characteristic polynomial, will be good, right? Because, if the transformation into this new intermediate form is something that only depends on the characteristic polynomial, and A tilde have the same characteristic polynomial, then it follows that this intermediate form should be the same for both of them, right? Okay, so let's kind of figure out what we should do. Well, let's start by constructing a transformation for A, okay? So for A, what we have is the Cayley-Hamilton theorem tells us we have if chi A equals S to the n plus an minus 1, S to the n minus 1, and so on and so forth, right? We have that A to the n plus an minus 1 plus A naught times the identity equals 0. Okay? So what I'm going to do now is I'm going to bring most of these terms over to one side and then multiply both sides by b. Okay? So first I'll have a to the n equals minus an minus 1, a to the n minus 1 plus, let me just do this as a minus a naught times the identity. Okay? So now I'll multiply both sides by b. So I have a to the n times b, a to the n minus 1 times b, identity times b is just b, right? So what can we do with this information? Well, maybe we can rewrite it in terms of the controllability matrix, right? You kind of see a lot of terms that look familiar to us from the definition of the controllability matrix. Let's try to do that. So if we perform this kind of controllability matrix rewriting of this expression, what we have is A times my controllability matrix B, AB, a to the n minus 1b will be equal to b, AB, a to the n minus 1b times this matrix 0, 1, 1, then zeros, a minus a naught, minus a1, all the way down until a minus a n minus 1, okay? Where, these first columns over here, these basically just correspond to collecting like terms on the left and right hand sides, right? So we have that this b term will correspond to ab over here and so on and so forth, right? Now this final term over here corresponds to this, which says that a to the n times b is going to be a linear combination of, these first n minus 1 powers, okay? So if we rewrite this more compactly, what I'll do is I'll say that this intermediate matrix is called M, right? What I have is that A times CAB is equal to CAB times M, or in other words, I have that A is equal to, what do I have over here? If A is equal to CAB times M times CAB inverse, right? Okay, very cool. So this gives us one piece of the transformation, right? Where do we go from here? Well, if we take a look at how we constructed this transformation, what we'll notice is that it only really depends on the characteristic polynomial, right? This new matrix M is something that only comes from a to the n plus a n minus 1, a to the n minus 1 plus all the way down until a naught times the identity, right? It's entirely parameterized by the coefficients of the characteristic polynomial. So what this means is that we can repeat for a tilde. Okay? So what this means is that we'll find a tilde is equal to c a tilde b tilde times m times c a tilde b tilde inverse, right? So let's go ahead, isolate m, and equate these two things. Maybe once we do that, we'll be able to work back this transformation from a to a tilde. Okay? So what we'll find is that, kind of by pulling out this m from inside this transformation, we'll get CAB inverse times A times CAB is equal to C A tilde B tilde inverse times A tilde times C A tilde B tilde. Okay? So if we want to work out this T such that we have T inverse AT is equal to A tilde, what do? Well, we can really just pull these transformations from one side over to the other, right? What we'll find is that C A tilde B tilde times CAB inverse times A times CAB times CA tilde B tilde inverse is equal to A tilde, okay? So what we do now is we define our transformation T as this term, and then we conclude that our A transformation holds, right? And when we're controllable, we can, in fact, get this transformation. Okay? Now we could do a similar process for B to show that, in fact, we have T inverse times B is equal to B tilde. Okay? So that completes the forward direction of this. The reverse direction follows from controllability matrix, rank, preserved under system transformations. Okay? So you can go ahead and check that as a nice exercise. All right. This also follows from this A tilde matrix being in controllable canonical form, and as part 1 says, controllable canonical form being controllable. All right, fantastic. So let's kind of summarize what we've shown so far. So what we've said is that, if our system AB is controllable, we can always find a transformation to put it into controllable canonical form, right? What we had said earlier is that once a system is in controllable canonical form, it's really easy to pick this K matrix to get our coefficients of the characteristic polynomial to be whatever we want, right? So by putting all these different pieces together, we can go ahead and say, okay, when our pair is controllable, we can go ahead and, actually stabilize our system via the state feedback A plus BK. So let's go ahead and summarize that results in a theorem. So this is theorem. This is called eigenvalue assignment. Now this is sometimes also called pole placement, right? Maybe you've heard it called this before. What we say is consider a pair AB where A belongs to Rn by n and B belongs to Rn by 1. Okay, so I'm still just considering a single input system. Then what we say is A comma B is a controllable pair if and only if for any collection lambda 1 all the way through lambda n, subset of C, where any complex lambda I come in conjugate pairs. What we have is there exists a matrix K in R1 by n such that the eigenvalues or spectrum of A plus BK is precisely equal to this collection lambda 1 through lambda n. Okay? So what we're saying is that our system is controllable if and only if we can put the eigenvalues of A plus BK wherever we want by choice of K. Okay? All right, let's go ahead and prove this result. So one direction of this result will really kind of require just sort of piecing together the things that we talked about up there. All right? So let's prove that direction first. So first, let's say, suppose I hand you a collection of eigenvalues and I'd like to find a K such that A plus BK has those eigenvalues. Okay? So let's say, suppose we're given a collection lambda 1 through lambda n of eigenvalues where any complex lambda i's come in conjugate pairs. So just as a quick side note, this conjugate pair condition is strictly required because A plus BK needs to be a real matrix, right? Real matrices always have their eigenvalues come in conjugate pairs. Okay, so what do we want to do? Well, let's try to figure out first what we actually want our desired characteristic polynomial to be. Okay, so our desired characteristic polynomial for A plus BK, if we want eigenvalues lambda 1 through lambda n, will be chi A plus BK of S simply equal to the product of factors containing each of these eigenvalues, right? So product I equals 1 up until n of S minus lambda I. Since if our matrix has eigenvalues lambda 1 through lambda n, then its characteristic polynomial will be exactly this product, okay? So let's just say for convenience, if we go ahead and we multiply this product out, we'll find that our characteristic polynomial is of the form s to the n plus some an minus 1 hat, s to the n minus 1 plus a1 hat times s plus a naught hat. Okay, so how do we actually work out, what each of these gains need to be in order to actually achieve this desired characteristic polynomial? What are we going to do? Well, what do we know? Well, we know that characteristic polynomials are preserved under transformation, right? That's the first thing that we know. And we understand characteristic polynomials and the relationship with K for systems in controllable canonical form, okay? So now, using the assumption of the forward direction that our system is controllable, what do we know? Well, from the previous result, we know that there exists a transformation T in Rn by n such that T inverse AT equals A tilde, T inverse B equals B tilde satisfies A tilde, B tilde in controllable canonical form, right? So what are we going to do? Well, first off, we're just going to go ahead and design for this system, right? Which we know will have, some sort of nice, easy to work with characteristic polynomial. So what I'll say is take a gain matrix, which I'll call K tilde in R 1 by n. Then I have that my characteristic polynomial chi a plus bk, a tilde plus b tilde k tilde, of s will equal the following. Well, it will equal s to the n plus a n minus k n minus 1, s to the n minus 1 plus a naught minus k naught. Okay? Where, this a n through a naught are the coefficients of my standard characteristic polynomial of a. Okay? So if I go ahead and do this, well, how do I pick k? Well, I pick k I such that ai minus ki is equal to my ai hats, okay? Where these ai hats are my desired characteristic polynomial coefficients. So effectively, under this choice of k, I'll have that this characteristic polynomial is exactly equal to the desired one, right? Plus an, that should be a minus 1, an minus 1 hat, s to the n minus 1 plus a naught hat, okay? So when we pick this particular choice of k, which matches each of these coefficients, then I get that my characteristic polynomial of a tilde plus b tilde k tilde is exactly my desired characteristic polynomial. Okay? So it now matches the desired polynomial. But this is still in the wrong coordinate system, right? This is still in this t transformed coordinate system. So in order to kind of pull this back to the correct system, what I'm going to have to do is, kind of invert this transformation. All right? So first what I'll do is I'll define a new matrix, which is k equals k tilde t inverse, right? So I'm effectively taking my gain matrix and then inverting this transformation. Now what I'll find is that under this gain, I'll have a plus bk will equal to t times a tilde times t inverse plus t times b tilde times k tilde t inverse will then equal to t times a tilde plus b tilde k tilde times t inverse. So then the eigenvalues of a plus bk and a tilde plus b tilde k tilde are the same. Okay? So effectively what we're doing is we're performing our design in this controllable canonical form, then we're using this transformation into controllable canonical form to reconstruct what this gain needs to be for my original system. Then by the fact that similarity transforms preserve eigenvalues, we conclude that this new gain over here, this gain k, actually gives us the eigenvalues that we want. Okay? All right, so that gives us the forward direction. Now let's do the reverse direction. So reverse direction, what do we want to do here? Well, let's say that, what do we want? We'll say that for all eigenvalues, lambda 1 through lambda n, subset of C, where the lambda i's come in conjugate pairs, there exists a matrix K such that A plus BK has eigenvalues lambda 1 through lambda n. Okay? So that's our assumption. Now what we want to show is that AB is a controllable pair. Well, let's say for contradiction, suppose AB is not a controllable pair. what does this mean we can do? Well, we know that, by this theorem we talked about in the previous couple of lectures, right, we can transform this system into its controllability form, right, where we can really isolate the controllable part of the system and the uncontrollable part of the system, okay? So then there exists a transformation matrix T in Rn by n such that I have T inverse AT equals A controllable hat, A12 hat, 0, A uncontrollable hat, and then I have T inverse B equals B controllable hat and 0, okay? So what does this form tell me? Well, this tells me I can only change the eigenvalues of my controllable block, right? A controllable hat. So why is this a problem? Well, I'm kind of claiming that I can place the eigenvalues wherever I want, right? If I can only do them on the controllable block, then that means that I can't assign n arbitrary eigenvalues for my system, okay? So what'll I do in order to get a contradiction? I'll pick a collection, lambda 1 through lambda n, none of which coincide with the eigenvalues of A uncontrollable hat, okay? Then by this controllability decomposition, what I conclude, there is no k that gives us these eigenvalues, right? Because what this transformation tells me is that I really have no hope of changing the eigenvalues of A hat uncontrollable, all right? So that goes ahead and gives us a contradiction, and we conclude that the result holds. All right, fantastic. So let's talk about our main conclusions. So conclusions is that when A comma B is controllable, and at least SISO, we can stabilize the system via static linear state feedback, right? U equals k times x, right? Because what this effectively tells us is that I can always pick a k to give me any set of eigenvalues that I want. So if I pick stable eigenvalues for a plus bk, I can find a k that gets me exactly to those stable eigenvalues, and I can therefore stabilize my system. Okay, so I want to talk about a couple of nice extensions of this result. So extensions. Now I'm not going to provide proofs of these just for the sake of time, but these are important, so I just want to discuss them quickly. Okay. So first is that this result holds for the MIMO case. Okay. So the proof is kind of similar, except instead of transforming your system into controllable canonical form, you transform it into a MIMO analog of controllable canonical form. All right. So it holds for MIMO systems. That's great. Now what else do we have? Well, we can also extend to stabilizable systems. Stabilizable systems, okay? So we can always pick k to make A plus bk Hurwitz when AB is stabilizable. Okay. So let me go ahead and just state kind of the general version of this theorem. Again, the proofs are fairly similar to the SISO case. They really just involve a lot more bookkeeping. And in the case of stabilizability, all that you do is you just perform this controllability decomposition and then prove that you could do control design for this pair, A controllable hat, B controllable hat. Okay? So let me go ahead and state this theorem. So this theorem, which is stabilization by static linear state feedback. What does this result say? Well, this says consider an LTI system with state equation x dot equals ax plus bu, where now we're considering the general MIMO case, right? Where A belongs to Rn by n and B belongs to Rn by m. Then if AB is a stabilizable pair. Or rather, let me state this as an if and only if theorem. And I have AB as a stabilizable pair if and only if there exists a K in Rn by n, in Rm by n, such that the closed loop system under the law U equals Kx, x dot equals A plus BK times x, is globally exponentially stable. Okay, so my system is stabilizable if and only if I can pick a matrix K to get this closed loop system to be globally exponentially stable. All right, so this proof is just a combination of the results above. Okay, and just the definition of Hurwitz implies global exponential stability. All right, now again, the MIMO case just requires a little bit more bookkeeping than the standard SISO case. All right, fantastic. So this main theorem really concludes our study of stabilization when we have kind of full information about the state of our system, right? In the case of full state feedback. Now what I want to do is I want to talk about a little bit of a harder problem. And this is output feedback. Output feedback. Okay? So in this case, right, whereas above we assumed that we had full knowledge of our state vector, this is really kind of infrequent, right? In the case of output feedback, we only have access to partial measurements of our state vector. Okay, so now if we have a state space system x dot equals ax plus bu with the output equation y equals cx plus du, we can only design a feedback controller using knowledge of your system matrices A, B, C, D, your output signal over all time, y of t, and let's say your input signal over all time, u of t. Okay? So now we have no idea what our actual state of our system is. Okay, so how do we actually go ahead and design a stabilizing controller in this case, right? Well, take a moment to think about this problem, see what you might do. Okay, so I'll assume that you've given this some thought, right? So one strategy for solving this problem is to see if we can estimate our state, okay? So we construct an estimate x hat of t of our true state. And use this estimate to do feedback control. Okay. So this is the basic idea of doing output feedback, right? We kind of construct this internal estimate of our state vector, and then once we have this estimate, we can go ahead and use that to do state feedback. If this estimate is really good, then maybe this will give us a kind of nice state feedback controller, or something that behaves like state feedback. Okay, so let's go ahead and let's kind of put a little bit more math down to this structure. Okay, so let's set up this structure in more detail. Okay, so basically what we have is we want to construct an estimate, x hat of t, and using this estimate we want to figure out an input to our actual system. Okay, so how do we do this? Well, kind of general setup and output feedback is the following. We have our system dynamics, right? X dot equals ax plus bu, and then y equals cx plus du. And then we have our controller block, okay? So this is our controller block. Now, this controller takes in the output, right, y, and then it goes ahead and it returns the input, u, to the system, okay? So contained inside the controller block, we have some estimator, x hat of x, and some control law using this estimate x hat. Okay? And then, using this estimate, we pick this input u, and then we send that to our system. Then the system sends an output y, and this feedback loop continues, right? So how are we actually going to figure out what this control law should be, right? How do we actually design this estimator? Well, there's a really interesting insight into this problem. Insight is that we should actually model our controller block as an LTI system, which we design, okay? So instead of just taking some sort of simple static state feedback law, right, which is kind of insufficient to solve this really hard problem, what we'll do is we'll say, okay, instead of just designing this simple gain k, what I'm going to do is I'm going to design a full I/O system, which is contained inside this controller block, all right? By picking the different matrices of this I/O system, I can go ahead and figure out what my input to my system needs to be, okay? All right, so let me kind of summarize this. So our controller block is determined by an I/O system, right? LTI I/O system, x dot controller of t is equal to a controller xk of t plus bk times the input to this block, which will be y of t, right? And then my output for my controller, which is just u of t, will equal some ck times xk of t plus dk times y of t, okay? So the input to my controller block is the output of my LTI system, and then the output of the controller block is the input to my LTI system, okay? So what I'm doing here is, something that's really super powerful, okay? So I want you to really kind of internalize this. Instead of just designing a control law u equals kx, I'm designing an entire LTI system to fit inside this controller block, okay? So this LTI system takes as an input the output of my true system, right? And as its output is the input to my LTI system, okay? So this controller is an LTI system, okay? So this is implicitly an LTI system. All right, so how do we actually perform this system design to kind of get what we want, right? We want to have this process of, being able to estimate my true state x and being able to use this state estimate to perform feedback control. Well, it turns out using something called an observer, we can get exactly this, all right? So we perform this process of estimation via this observer system. And then using this observer system, we can construct a control input, and therefore this entire LTI controller block, which gives us the property that we want. Okay, so let me go ahead and state a theorem about when these observers, which kind of estimate the state of our system, actually exist. It's called theorem existence of an observer. Okay, so we'll say consider an LTI system, which I'll call x dot equals ax plus bu, and then y equals cx plus du, okay? Now here we're going to have the MIMO case, which is a belongs to Rn by n, b belongs to Rn by m, c belongs to Rp by n, and d belongs to Rp by m, okay? Then the following will hold. Well, first, what we'll have is that A, C is a detectable pair. Remember, detectable is kind of the analog of stabilizable, but for observability. It's a detectable pair if and only if there exists a gain matrix, L in R n by P, such that A plus LC is Hurwitz. Okay, so again, I'm just going to state these results for now. We'll kind of discuss what they mean in just a moment. Okay, so just sit tight for a sec. Now, 2, what do we have? We have that if L is chosen such that A plus LC is Hurwitz, then the system with state equation x hat dot of t equals A plus LC x hat of t minus L times y of t, where y of t is the output of my full system, right? Plus B plus LD times U of t is such that the limit as t goes to infinity of x of t minus x hat of t equals 0 for all initial conditions, x hat of 0 and x of 0, okay? And we say that such a system is called a Leuenberger observer. Leuenberger observer. Observer of our state. Okay, so let me summarize what this system is saying, or excuse me, what this theorem is saying. So above, we had kind of said, okay, if we could design this controller block via this, nice fancy design technique, which is design an LTI-IO system that gives us what we want, then, maybe we could solve this output feedback problem. And what we said was that, inside this controller block, we kind of need a couple different pieces, right? Now, our first piece was an estimator of our state, x hat, and our second piece was some control law using x hat, okay? So this theorem says that we can kind of do the first piece, all right? Using the information of the input to the system and the output of the system, we can actually figure out, a nice way of estimating our state asymptotically, okay? So we're guaranteed that we get asymptotic convergence of our state to the origin. And the first part of this result says that, we could do this asymptotic detection whenever A, C is a detectable pair, all right? Okay. So let me go ahead and kind of give you the proof of this result. So part 1, which says that AC is detectable if and only if there exists an L such that A plus LC is Hurwitz. This is something that follows directly from duality, okay? Now you might remember from last time that what the duality result effectively says is that AC will be observable if and only if A transpose C transpose is controllable. Now we could state an analogous version of this for detectability and stabilizability, okay? And this is that AC is detectable if and only if we have A transpose C transpose is stabilizable, okay? So then what you do is you apply your state feedback gain selection theorem, which uses stabilizability together with duality, and the result follows, okay? So you might notice that over here we have A plus LC instead of A plus C times L, which is kind of more like the setup that we had before. And the reason this L and the C flip is because we're now taking the transpose, right? Okay, so that's part 1. This is effectively a duality argument, right? I won't spend a huge amount of time discussing that. Now part 2, I really want to kind of focus on motivating this, seemingly rather arbitrary expression that I've given you up here, okay? So what do I want to do? Well, I want to design a system with a state equation such that the state of that system converges to the state of my true system, okay? So how am I going to do this? What am I going to do? Well, what we can do is, if we want this convergence between x of t and x hat of t to go, down to 0, we can kind of define a system kind of around the error between x and x hat of t, okay? So what we'll do is we'll design a system around your estimation error. Which I'll call E equals x hat minus x, okay? Now the dynamics of this system should be such that, when we perform this estimation and we kind of compute the derivative of this estimation error, pretty much all of the terms kind of drop out, right? Except this error term x hat minus x. And it turns out if we want all of the non-x hat minus x terms to drop out, this system up here with x hat dot equals a plus lc x hat minus ly plus b plus ldu is exactly what we need, Okay, so let me go ahead and show that. So let's go ahead and compute E dot, okay? Well, this is equal to x hat dot minus x dot. Now, if I substitute in this expression up here, what we'll find is that this is equal to a plus lc times x hat of t minus l times y of t, which is equal to cx of t plus d times u of t, plus b plus ld times u of t, and this is going to be minus ax of t plus b times u of t, right? Because that's the derivative of x. Okay, where do we go from here? Well, let's see if we could figure out what sort of cancels out from this system. Well, right away we notice that this, d term over here, oops, sorry, I wasn't using my highlighter term there. So this should be a d times u of t. We'll have this term, right? And then this ld times u will go ahead and cancel out, right? We go ahead and we perform all these different cancellations, right? What we'll find is that this guy will be equal to a plus lc times x hat of t minus a plus lc times x of t, right? Once we cancel out all of these miscellaneous terms. Now, if we just factor out this a plus lc, then we'll get a plus lc times x hat of t minus x of t will be equal to E dot, or in other words, E dot equals a plus lc times E, okay? So as a consequence of this, if we pick L such that a plus lc is Hurwitz, then we get E of t goes to 0 exponentially fast from any initial condition, right? So effectively what this confirms is the second result, right? If we use this estimator, or this Leuenberger observer, as we're calling it, and we pick L such that a plus lc is Hurwitz, then our estimation error will asymptotically go to 0. Okay, fantastic. So this is kind of the first piece of our, kind of nice and fancy controller block, right? This gives us this first part where we estimate our state using this new term x hat. Now what we need to do is we need to figure out what the output equation of my controller block should be. Okay, let's go ahead and do that next. So what do we want to do? What to do next? So what do we want to do? Well, we want to use our estimate x hat of t to stabilize the system. Okay, what we've just shown is that we actually get really, really good estimation of our true state x of t via this Leuenberger observer estimate x hat of t, right? So the basic idea is we design a controller u equals k times x for our system as if we had full knowledge of our state x, okay? Then all that we do is we just substitute in our full knowledge x for our, substitute in our estimate, not our full knowledge, estimate x hat for our true state x, okay? So we pick the control law u equals k times x hat. And, since above we kind of showed that we get this really excellent asymptotic, in fact, exponential estimation of our true state, maybe this is going to be good enough, right? If we design assuming that we had, full knowledge of our state and we know that we can get our estimate to be really, really close to our true state, then maybe just substituting in estimated state for true state in this control law will actually give us a stable system. Okay, this, following result, which is kind of a really nice, important result in control, called the separation theorem. Separation theorem tells us that we could do exactly this, right? First design a stabilizing controller, then design a stable estimator, put the two together, and we get a stable output feedback system. Okay, let's go ahead and state this theorem. So we'll say, consider the linear time invariant system representation A, B, C, and D. Okay, it's a MIMO system. Then we say that the closed loop system, defined by the state equations, x dot of t, x hat dot of t equals m times x of t, x hat of t, which is defined by the equations, our normal state and output equations, right, which are x dot of t equals ax of t plus bu of t, then y of t equals cx of t plus du of t, then our observer, right, which is x hat dot of t equals a plus lc times x hat of t minus ly of t plus b plus ld times u of t, and then u of t equals k x hat of t, right, which is our control using our estimated state. This system is such that the eigenvalues of this matrix M, the spectrum of M, is simply equal to the eigenvalues of A plus BK union with the eigenvalues of A plus LC. Okay? So what this result effectively tells us is that if we design a controller, so controller based on your Leuenberger observer. So if we design a controller based on a Leuenberger observer, right, which has eigenvalues A plus LC, and then we design some nominal controller for our system, which has eigenvalues A plus BK, then the eigenvalues of the entire system, right, with our controller in closed loop with our original system, has eigenvalues of A plus BK and the eigenvalues of A plus LC, okay? So the basic result of this is that if we pick L such that A plus LC is Hurwitz, and we pick K such that A plus BK is Hurwitz, then we get that our full output feedback system is in fact stable. All right? Okay, let's go ahead and give a proof of this. Proof. Okay. So first what I'm going to do is I'm going to go ahead and really just rewrite these systems in terms of this matrix M. Okay? So first, let's solve for your matrix M. Okay? What are we going to do? Well, let's kind of sort of figure out what the equation for x dot should be first, right? So I have x dot of t equals ax of t plus b times u of t. Now what's u of t? This is equal to ax of t plus bk x hat of t. All right? So this gives me x dot in terms of the state of the full system, x hat. Okay? Now where do I go from here? Let's try to figure out the equation for x hat next. So I have x hat dot of t is equal to a plus lc x hat of t minus l times y of t, which is c times x of t plus d times u of t plus b plus ld times u of t. If I go ahead and do some simplifications, right, what I'll find is that this is equal to a plus lc x hat of t minus lc x of t plus b times u of t. Then I go ahead and I substitute in for u of t. This is equal to a plus lc plus bk, where I'm just kind of cleaning up this formula a little bit, times x hat of t minus lc times x of t. Okay? So what I've just done is I've gone ahead and I've solved for x dot and x hat dot, which is the state of my full system, right, where my controller block and my LTI system block are put together. I've solved for these in terms of each other, right? What this tells me is that I have x dot of t, x hat dot of t is equal to a matrix times x of t, x hat of t. And that matrix will be first a times x of t plus bk times x hat of t. right? That gives me a bk up here. Then over here I have a minus LC term. Then I have an A plus LC plus BK term down here. All right? Okay. So what we've just done is we've gone ahead and we've solved for this matrix M. All right? Now I just want to transform this matrix M into a form where it's really, really easy to go ahead and actually kind of compute what the eigenvalues of this M matrix are. Okay? So what we'll do is we'll define the transformation, which is going to be T equals identity minus identity, 0, and identity. Okay? And if you go ahead and you compute T times A minus LC, BK, A plus LC plus BK, multiplied by T inverse, what you'll find is that this is equal to A plus LC, 0, a minus LC, and an A plus BK. Okay? So since similarity transforms preserve eigenvalues, what we conclude is that the spectrum of M is simply equal to the spectrum of A plus LC union with the spectrum of A plus BK. Okay? Since these are simply these diagonal blocks over here, right? A plus LC, and then the other diagonal block, A plus BK. All right? And that's a proof. So let's kind of figure out what this theorem is telling us. What this tells us is that if we pick K such that A plus BK is Hurwitz, and L such that A plus LC is Hurwitz, then the full system, which is x dot, x hat dot, equals this matrix M times x, x hat, is such that M is Hurwitz. Okay? And as a result of this, we get that x of t goes to 0 for all initial conditions. Okay? So what this result tells us is that using this output feedback control law, right, this fancy controller block, which has a Leuenberger observer, which estimates my states, and then an output control law, which uses this Leuenberger observer estimated state, I can actually stabilize my full system. And the key part of this is we can design the observer and controller separately. Okay? That's what gives it the name separation theorem. Now, this does come with a couple of caveats to do with robustness, which I'll talk about in just 1 minute. Okay? All right. First, I'll just go ahead and state a corollary of this theorem, which is stabilization via output feedback, right? So I'll say, consider an LTI system, representation A, B, C, D, where A, comma B is stabilizable, and A, comma C is detectable. Then what can I say? Then there exists a feedback gain, K, such that A plus BK is Hurwitz, an observer gain, L, such that A plus LC is Hurwitz, and finally, such that the origin of the system x dot, x hat dot equals M times x, x hat is globally exponentially stable. Okay? So what we're saying is you design a feedback gain K such that A plus BK is Hurwitz, design an observer gain L such that A plus LC is Hurwitz, then you get global exponential stability of this full composite system. Okay? And the proof of this is really just combine the results proven above. Okay? All right. So what we've said is that as long as a comma b is stabilizable and a comma c is detectable, we can always do this output feedback solution. Okay? So what are caveats, if any? So what are caveats? Well, let's think about a couple things. Well, first, this was entirely deterministic. Okay? So Leuenberger observer has no random noise. Okay? So we haven't said anything about stochastics, right? Which commonly come up when you're doing a state estimation problem and you have noisy sensors, right? So what happens if we were to do this case of random noise? Well, case of random noise. If the noise is Gaussian, what you'll commonly find is that people use a Kalman filter. So this is an extension of the Leuenberger observer. Okay? So what goes on if you go ahead and you use this Kalman filter in conjunction with an optimal state feedback law? Well, this leads you to something called LQG. Okay? So this is optimal. I'll put optimal in quotes because I haven't really discussed what I mean by this. State feedback law with optimal observer. And this might sound really good in principle, right? But the problem is it has very poor robustness properties. Okay, so this is proven in a paper by Doyle. All right, so effectively the idea of LQG is that if you have really, really good state estimation on really bad data, okay, then your overall system will not have desirable results. Okay, so if you're optimal on really bad data, that doesn't mean that your system will have good performance. All right, so that's kind of a caveat that you should keep in mind whenever we're doing this estimation, right? This Leuenberger observer, although it really seems to give us a lot, it can't really work with stochastic behavior, right? Or at least we haven't explicitly accounted for stochastics. In the case where you do account for stochastics, you end up with robustness properties, right? Where, you have bad measurement data and you're optimal on that bad measurement data. That means that your overall system will kind of have poor performance despite having optimality on both fronts. Okay? So we'll talk about this a little bit more next week when we discuss LQR. All right. Thanks for watching.